generics-sop, which is a library that I've written together with a colleague of mine, Esther de Vries. Yeah, so it's about data type generic programming in Haskell. So let's see how much you already know. So who of you has ever used a deriving clause in Haskell? Right. So you've all been using some form of data type generic programming, so that's good. So you're all not beginners. Who of you has actually worked with, say, GHC generics? Okay, that's actually quite a few. And something like scrap your boilerplate or any other unique place, whatever. Okay. So generics-sop is a library which is essentially in that area. So it aims to give you a way to do data type generic programming. What does that mean? It aims to give you a uniform yet still typed representation of data types. So, so that yet typed differentiates it more or less from template Haskell. With template Haskell you can get some programmatic representation of any Haskell program, and then you can do anything what you want. Data type generic programming is much more restricted in the sense that you can do fewer things, but it gives you a richer structure of data types on which you can still operate in a type-safe way. And then it basically represents these data types as another Haskell data type that you can work on uniformly. And then generics-sop specifically gives you a whole bunch of higher order functions that allows you to conveniently work with these representations. And then you can use those higher order functions to compose functions that are generic in the sense that they work with many different Haskell data types, more or less out of the box. So, yeah, so the library is available on Package. It's also available on GitHub. And yeah, it's like sort of originally mostly developed by Etzko and me, but by now there are quite a few other contributors. Specifically, I want to name Oleg, who has been contributing quite a few patches recently. And it's used in production, so I wouldn't say it's very widely used. I don't actually know how many people outside of well-typed are using it, but we have a number of projects in which we are actually using the library, so I would consider it stable for day-to-day use. Okay. So the basic idea is that you're given a representation of the type A that is some other form of a value of type A, which is this uniform representation that you can work on in order to write generic functions. And this representation of A is actually isomorphic to the original type A. You're given functions from and to that witness this isomorphism. So you can, for everything that is in the generic class, apply a function from to a Haskell value and get the representation of that value, and then you can operate on that representation, and when you're done, you can apply a function to get back an original value. And now, different generic programming libraries choose very different representations. The one that generics-sop uses is called SOP, and that's for sum of products. And that's this type here. And then there is this I, which is like an identity functor. I'll go into that in more detail. And it's an indexed structure, so it's for those of you who know this, it's a GADT, which is parameterized over something which is called the code of A. And actually, I want to briefly look at what this code is, because that gives you an idea of how this all works. So let's actually jump into GHCI for a moment, and I can make this a bit larger as well for the time being. So the code is a type family, and GHC has this not very logical command kind bang in order to like evaluate type families on the command line. And so we can look at what, for example, is the code of the type bool. And you'll see that codes are of kind list of star. So that's there's a lot of type level programming in this library. So these are type level lists. So just like normal lists, but they live on the type level. And there are lists of lists. And the elements of the inner lists are of kind star. That means the elements of the inner lists are actually types. And the idea is that you have a essentially two-dimensional table, and the outer list contains an entry for every constructor. So that's why this list that you're getting here has two entries, because Booleans have two constructors, false and true. And the inner lists contain an element for every argument of each constructor, describing what types they have. And now Booleans have two constructors, false and true, none of which have any arguments. That's why the two inner lists are empty. If we look at something like maybe int instead, we see that, okay, a maybe int can be either nothing, that's the first case. So we again have one constructor that has no arguments, or it can be just of an integer. And in that case, we have a constructor that takes an integer as an argument. And that's the second list. And we can also, for example, look at a list of integers. There we see that, again, actually, oh, I wrote maybe list of integers, that's why I'm surprised. I wanted list of integers. So for list of integers we get an empty list because that's the nil constructor, and we get the const constructor which takes an int and a list of int. By the way, there are all these little quotes. If you haven't seen type level lists very often, this is the reason why you have them. So the quote in front of a type level list means that it's actually a type level list rather than the list type. And here you see that we have list of int occurring as a type, right, and not as a one element type level list. And that's why you have to disambiguate this. And it's a bit unfortunate that the syntax of Haskell in that space is already so crowded that you have to resort to rather ugly hacks in order to make things unambiguous. Okay, so these are the codes, and then essentially we have two sorts of data structures in generics-sop: sums and products. And so if you have a type level list, something like, I don't know, apple, oranges, and bananas, and you have a product, then you have to provide one of each, right? You have to provide an apple and a banana and an orange. And if you have a sum, you have to choose one. So you have to provide either an apple or a banana or an orange. And essentially products are lists, heterogeneous lists, pairing up everything that is in the type level list that they're indexed over. And a view of sums is more like a number paired with a payload. So you're choosing one of n elements, so you essentially get an index from 0 to n minus 1, representing the choice, and then you still have to provide that particular element. And that basically explains what happens if you look at what actually you get if you apply from to something. So if I apply from to the integer 3, I'll get this sum of products representation. And the 0 of successor here, that's a number, that's a 1 that essentially encodes that we're not choosing the first, but the second constructor, which is just. So the first constructor would be nothing. And then the payload is a product. And the product is essentially a list which contains just one element, which is the 3. Okay? And then there is this added feature, if you like, that every one of the inner elements doesn't actually have to be the element itself, but it can be parameterized by an arbitrary type constructor. And the thing that you're getting back from is always parameterized by the identity type constructor. But we can use this to interesting effects. For example, if we want to map every element in a data structure to a uniform type, but maintain sort of the number of elements on the type level, we can swap out this identity type constructor for a constant type constructor, and then we can just keep the same structure, but put ints everywhere, or put strings everywhere, or something like that. Or if we want to perform an I/O action for every element in a type, we can swap out this I for I/O, and then we have things wrapped on I/O. So that's just coming in useful. Okay. Let's get back to this. So if you actually want to work with a data type in this setting, you have to make an instance of this generic class of the generics-sop library. And that's a different generic class than the one that GHC already provides. But the nice thing is that you can derive the SOP generic class from the GHC generic class. So in H21 and GHC H21, derive any class finally works more or less like I wanted to, thanks to the hard work by Ryan Scott. And you can essentially just write it like this. You have to derive the GHC generic class in order to be able to derive the generic and the has data type info class, but you can just write them all down in the deriving clause and you'll get them. Alternatively, you can also use template Haskell to derive the SOP generic class. These two mechanisms are more or less the same. But if you have your own data type, you can make it an instance of generic in this way. For all the data types in the base library, the library, the generics-sop library, provides generic instances already. That's why we could use from on maybes and on lists. But now I can, for example, also say, if I have this direction type, from north is just the first constructor, and it has no arguments. And then if we do from on south, that's the third constructor, so it has an encoded 2 here, and it still has no arguments. And what was the other one? Int tree, if I do a from on a node of leaf 3 and leaf 5. Again, we have the first constructor of the tree data type, and 2 arguments, one being leaf 3 and one being leaf 5. One thing to notice here is that it's only a one-layer transformation, right? So trees are recursive, and they have a left and a right subtree, and the left and the right subtree appear in this representation in their original form. So that is actually very useful for many things. It's also more efficient because often, basically, if you operate on a data structure recursively, you apply the transformations as you need them layer by layer, but you don't have to go all the way down and transform everything if you don't actually need to operate all the way down. Okay, so that's that. Then, as you see, the structural representation doesn't give you any information about the names. And often this is a good thing, because many things that you want to write generically, things like equality function, comparison functions, I don't know, traversals over your data structure that modify something here or there, they don't actually care about this metadata, and you want to ignore it as much as possible. But sometimes you need it, in particular for one of the often used things is serialization and deserialization. There you often want to somehow make use of the record field labels or of the constructor names in order to generate the right representation. So that's what this has data type info class is for, which is separate, but basically provided for all data types as well. And that gives you structural information about the names involved. So we can actually look at that. The data type info of, let's look at our direction type looked like this. So this is giving us the GHC representation as well. I didn't actually want that. So the definition of the direction data type was just a simple enumeration type with 4 values. And if we look at the data type info of direction, so we need to provide proxy in order to actually help GHC figure out for which data type we mean this. So intuitively we could use an explicit type argument here, but I still want to remain backwards compatible with versions that didn't have this, but I can do this. A proxy of direction. Oh, I need to enable. And then you'll see that you'll actually get information back like this. Is defined in the module SOP, which is the module I'm working in here. The name of the data type is direction. And then you'll also get a product. So this is the product again of constructor information items, where the first you see that it has exactly 4 entries. And actually this is sort of type safe again in the sense that this is indexed by the code of the data type. So you're guaranteed that if the code of the data type says that the data type has 4 constructors, then this list will also have 4 entries. This gives you the names of the different constructors.
So if the ordering changed in our subtitle would be swapped, like the ordering of the constructors?
Yes, yeah. So the order is the order in which they are declared. Yeah, sure. If I don't know, swap west and south, oh, this will bite me, but because I probably will type in something differently. But yeah, then that changes here as well. Okay, so now let's actually write a generic function. So this is a simple generic function that just gives me essentially what's already contained in here, but in a sort of less cluttered way. Just a list of all the constructor names of a data type. So rather than having this additional information surrounding it, where also the data type name is contained, and actually also rather than having these constructor thingies here, which possibly can contain additional information if it's an infix constructor or something like that, we simply want to have the names only. And so this shows us sort of how we can work with these products and sums. So we have the data type info function from the library, which given a proxy gives us a data type info value. And we also have a constructor info accessor that is provided by the library that gets the product of constructor info out. But that's still a constructor info and not constructor name. So we also have a function that takes a single constructor info into a constructor name. And what we would like to do is just essentially map over the product and change every instance of constructor info into the constructor name by mapping this constructor name function over the product. But the product is a heterogeneous list, right? It's not a normal list, so we need a different map function. We cannot use a normal map function, but this is one of the functions that is provided by generics-sop. So we can use a map over an NP, an NRE product. And what is the product we want to map over? Well, that is the one that we get by applying the constructor info function to the data type info of the type that we're interested in. So we're getting this proxy A argument, which we just pass on to here. And then, let's see. And then the function that we map has to be of type constructor info A to K constructor name A. K is this constant type constructor, so we're getting a product out which, as I said, in every position has a constant constructor name. And the original one is a constructor info of A, but that just fits the constructor name function. So the constructor name function just takes a constructor info indexed by anything and extracts the name. So, so we can take constructor name here. And, oh, it doesn't fit it exactly because we have to go K constructor name. This just gives us a constructor name, so we actually have to do K after constructor. Okay, that touches. All right. So next example is we want to get the name of a particular. Oh, let's try it. Not just believe it. Constructors of direction. Oh, yeah, sorry. That's the next one. That now really just gives us the product of all the names without the rest of the cluster. So now the next one is to get the name of a particular constructor, namely the constructor of the value that we are giving it. So that's a little bit more interesting. So we only want the name of the constructor that constructed that particular value, the top level constructor, as a string. Okay, so how are we doing this? Well, so I'll actually just, because I'm relatively short on time, just show the definition and explain it. So what we're doing is we first construct the representation of the value, and we take the list of all the constructors that we just defined. So the list of all constructors that we just defined is a product containing n entries if the data type has n constructors. And the representation is a choice of one of these constructors and the actual arguments of the constructors, which we are not interested in for this function. And then we combine these two things. So we have an n-array product, and this thing is a sum, an n-array sum of n-array products. And we can, in the library, even that's perhaps a bit misleadingly called zip with as well, we can zip two products that have compatible length. But we can also zip a product with a compatible sum. And what does it do then? I mean, if the product gives you a choice between n things and the sum makes a choice between these things, then that simply makes the choice in the product, so picks the corresponding element out of the product, and combines these two things together. So what we're doing here is we're using the representation of the value to pick the right element out of the constructors table. And then we're combining them in such a way that we get the name, the chosen name out of the constructors. That's the constructor name that we're interested in. And we also get the payload from the sum, which is the arguments of the constructor that this value has. But we are not going to do anything with them. And we're just going to return the name of the constructor. And, oh yes, and then after having done the hzip with, we actually get, let's see what the type of this is. It's a sum. So if we combine an n-array product with an n-array sum, we get an n-array sum. So that's a sum that contains just a constructor name. So it still retains which constructor it was as a number, if you like, but we are no longer interested in that number, we are only interested in the name. So we can use this hcollapse function, which was there, which we can use on any structure that contains constant values to essentially get all the values out, either as a single element for a sum or as a normal Haskell list. And let's look at this as well. So if we actually take constructor north, need to reload, then I get north. If we take constructor south, I get south as a string. Perhaps a little bit more interesting is doing something like this. That's x, I get just as a string. If I do 1, 2, 3, what do I get?
Please testing.
Cons, yeah, actually without parentheses in this case, so that's something that's a choice by the library. The name of the constructor is just printed. But yeah, cons is the top level constructor. So that's this one. Okay. One more thing I can do is I can, because I have the codes on the type level, I can make restrictions about the shape of the types that I want the function to work on. That's something that I cannot usually do with most other generic programming libraries. So in particular, the most frequently used ones, I think, are you want to restrict the function to work only on record types, or you want to restrict the function to work only on enumeration types. Record types are types that have a single constructor, or perhaps I should say product types. I mean, there is perhaps yet one more distinction that's interesting, like you want functions to work on types that only have a single constructor, and sometimes you want functions to only work on types that have a single constructor and actually have record field labels. You can make that distinction actually. But and then the other enumeration types are types where every constructor has 0 arguments, essentially. None of the constructors have any arguments. And so there is a predefined type constraint for that, is enumeration type of A, but if we look at how that is defined internally, it's actually a shorthand for saying A has to be generic, and that all is also something which is defined by the library. All the elements in the list, in the outer list that is given by code A, have to be equal, that's type level equality to the empty list. So that's what we saw in particular hold for bool, sorry, code of bool. Right, all the elements in the outer list are equal to the empty list. And that also holds for direction, which is another enumeration type, or it holds for ordering, which is another base library enumeration type. Right? So so these codes fulfill this constraint. And now I can restrict my constructor function to only work, if I like, I mean, to only work on enumeration types. So so I can say constring on a value of type direction, east. That works, but I can no longer use it on a value of type list. Then I get a type error. Not a very beautiful one, but at least one that does make sense within the context of the library. Okay, so this doesn't make use of, I mean, this is just an arbitrary restriction, but now something where we can actually use this is this function which I want to write enum to obtain all values of the data type. But I want to keep it simple, and because I'm almost out of time, to do it only for enumeration types. Of course, it's an interesting data type generic programming to enumerate infinite types, but enumeration types are extremely easy to enumerate. We just want all the values. Okay, and so here we are actually going to use this constraint, this enum type constraint. So, so the first thing is like, how do we create values in the first place? And so intuitively, generics-sop provides a very interesting function that's called injections. And injections, I can show that. Injections is just a product of injections. What does it mean? Essentially, these injections that you're getting are is a product of the length of the code. So for every constructor, you're getting one injection function that you can apply to suitable arguments of that constructor in order to create a value of that constructor. So essentially, injections gives you a function, a product that where the first element constructs a value of the first constructor of the data type, and the second element constructs a value of the second element of the data type, and the third constructor constructs a value of the third, and so on. So ultimately, you get exactly, well, almost exactly what we want, because we want a product containing all the values of the data type constructed by the different constructors. But the problem is that injections still expects the arguments to the constructors. And in order to apply the injections to their arguments, we have to supply the arguments. And if we need arguments for all the constructors, then we actually need a two-dimensional table, right? So we need as many lists of arguments as there are constructors, and then every list of arguments needs to be exactly as long as the arity of the constructors. So that's a product of products. And because that's an often used combination, this function that applies the injections to a product of products is already in the library. So this is taking a product of products, that's just a shorthand for product of products, and interprets this as all the arguments to all the constructors, and then it applies the injections to it, giving us a single product again, where in every element we have a constant value, which is just of the representation of the original data type, essentially, of the sum of products representation of the original data type. And then you could imagine we can apply the transformation 2 to this sum of products in order to get back the original values. Now we still have to come up with this product of products, but we have chosen to restrict ourselves to enumeration types. And the enumeration types do not actually have any arguments. So how do we create a two-dimensional table of empty lists? And so in the normal homogeneously typed Haskell world, if you had to create a list with a number of times the same element, you would use something like replicate or repeat, right? And if you've ever heard of sort of the zip list instance of a applicative, you might know that this is sort of the pure of the zip list applicative, actually. So there's a relation to, you can sort of see vector operations or list operations that are performed pointwise as in having an applicative structure, and then the pure is just the repeat, and the star is just pointwise application, zip with apply. And that's why the function in the library that does this is called pure. So we can use, let me go back to, we can use this cPureNP function to construct a vector, essentially a heterogeneous product of empty lists, and the deal actually of empty lists. And in order to do that, we have to use, on the type level, the fact that we know that every list is empty, because otherwise it wouldn't be type correct to produce nils here, right? So that constraint is now essential in order for this to be type correct. And we actually need to help GHC along a little bit by providing sort of the constraint that we're using in order to be allowed to construct this. That's why there is this C pure NP function for constrained pure NP, where we have to pass a proxy of the constraints that we're using, because GHC's type inference is very clever, but not clever enough for this particular case. So it cannot infer the constraint that we meant automatically, unfortunately. So we have to tell it that we want to use the equal to the empty list constraint at this point in order to create this product of empty lists. And then we have this product of empty lists. And then we can apply the injections. And then we can, as I said, ultimately map the two functions over them in order to get the original values out. So let's see if this actually works. Oh, because I still have undefined up here. So if I call enum on, so what was the type of enum? Yeah, I either have to give a type annotation for the result type, or I have to use a type application to say which type I actually want to enumerate. So the type annotation is more complicated, so I'll just say I want to enumerate the direction type again. And I haven't reloaded. That works. Now I get the list of all the values, right? Not the list of all the strings anymore, but the list of all the values. So I actually get a product containing north, east, west, and south. And since all of these are of the same type, and it's a product of constant values, so I can actually use h-collapse again, which we've seen before, or the specific version on products, which I've used here. So for everything in the library, there is an overloaded version that works on sort of products and sums of products and products of products as far as possible, but there's also a specific one if you want to be more precise. That gives you the actual list of values. So let me hold this. Okay. So this is a whole lot of things, but I basically want to stop here. I just want to reflect briefly on what I've shown. So it sort of gets rather involved in the type level, but at the same time this is also rather attractive because you can be very precise about the types and you can write things that are still very type safe. Ultimately, I think it's compelling because you can write functions like this generic enumeration function in essentially one line of code by reusing other higher order data type generic functions and combinators provided by the library. If you compare that to sort of the standard way that you write stuff in GHC generics, you would write like 7 or 8 class instances that would extend over 2 or 3 pages, even for a simple thing like this, and you would never actually reuse any code. So that's the sort of primary difference in style. And the other nice thing is that you can constrain, as I said, that you can constrain the shape of the data types that you work on and actually make use of that fact. And there are many other things that you can do with this that I haven't shown. For example, you can use the fact that you have these data structures of products and sums to provide extra user-defined metadata that you can use in a type-safe way. So for example, if you have a serialization function which shouldn't use the original constructor names, but some domain-specific other constructor names, you can like sort of take as an extra argument a table of just the right size that has exactly the right number of user-defined constructor names and take those into account. Yeah, so other things that I haven't shown is that like since the 0.3 release of generics-sop, type level metadata is actually available. So the metadata that we looked at here was just all values, but you can actually now also use metadata on the type level, and you can use this for doing things like implementing record subtyping or name-based accessors, where you basically use a record name on the type level to select a particular component of a product or a particular component of a sum with the name of a constructor. And well, that's there are a number of very interesting applications possible with that. And yeah, I'm also still working on a data type generic migrations library, which is based on this, but it's sort of continuously stalled because I have little time to actually work on this, and it's not on a critical path for me, so it's just a hobby project at the moment, and I don't need it very dramatically for anything. That means that other things always have a priority. But I am going to work on generics-sop and the library this weekend. There are quite a number of things to do, including more easy tasks. I mean, documentation can always be improved, but there is also a very dramatic need for doing proper benchmarking, because I actually have sort of 3 different branches playing with different ideas to possibly make things more efficient, but I currently have no code in place to actually measure the comparative efficiency of the different approaches. So I cannot actually tell which one of the 3 is best, or if they make any difference. So I'm more interested in thinking about these ideas of making it faster than actually measuring it. But so if anybody is interested in helping me to actually measure the performance, that would be very welcome. And I'm sure there are other interesting tasks to work on as well. So if you want to help me with that, I'm here all of today and most of tomorrow. Okay, thank you.
Do you have questions?
And so can I write, or at least easily write, recursive generate functions and recursive data types? Because as we've seen, this is just a one level generic unloading of any type.
Oh yes, but that's not a problem in practice. So yeah, I mean, the answer is yes. I mean, you just...
So for example, but then I will have to sort of determine where the recursion occurs, and I can do that by some kind of equality checking on the type level.
No, so the typical way to do this is, like if we take, for example, something simple, like the show class. Let's assume we want to implement our own show method, and you have a recursive data type. Then you would define a class.
Then I would essentially have recursive instance for show. That would be
yeah, exactly. Now you would define a class which has a method show that takes an a to a string, right? And then you're basically saying that in order to make, say, a tree a string, you need to know that, essentially, or let's just phrase it generically immediately. In order to make a data type an instance of the show class, you have to know that all the types that occur as arguments of any of the constructors are also in the show class, right? But that's okay, so then you get sort of a recursive constraint or like in the case of a recursive data type, so basically say I can only make trees into an instance of the show class if trees are an instance of the show class, but they will be, so that constraint is satisfied. So that's not a huge deal. I can show you, but showing you like sort of in code probably takes too long right now. It'll probably take another 5 minutes or something. So but I can show you.
You can work on the also as a project. So during the day you can work on it. So you can see.
Okay, so but my sort of other question would be so we could alternatively work with functors, sums and products of functors, and then have explicit fixed points.
Ah, yes. Okay.
Or even work with index functors and then have mutual data types.
Yes.
But so I guess the experience is that this is not the need for the common use cases.
Right, so actually, I mean, I have been working on data type generic representations that are based on fixed points or functors, or even index fixed points or functors as well. There are there are some use cases where this is useful. In particular, if you want to, I don't know, derive a fully generic version of a catamorphism or of an anamorphism or something like that, that works over all data types, where you sort of the function really needs access to or knowledge of where the recursive positions are. But you're also paying a relatively high price because indexed functors and indexed fixed points are no joke. I mean, they're adding an extra level of significant complexity to the representation, which is already reasonably complex at this stage. So, and for most things, you don't need this. I mean, if you sort of have normal behavior on the recursive cases and sort of unfolding gives you just what you want, and you don't need actual knowledge about is this a recursive position or does it just normally happen to be there, then you can avoid all this extra complexity, and then this kind of representations are more convenient to work with. So I have found, I mean, I find these other approaches compelling from a theoretical view, but then sort of in terms of practical needs, I've found relatively few examples where they are truly needed.
Does this representation work for types that are GDPs?
That's a good question. No. I have some ideas, but like representing GADTs using any kind of generic representation in a very convenient way is still at least to some extent, I would say, an unsolved challenge. We can certainly talk about this a little bit more as well. I mean, I would love to have a better story to tell there. So.
I have another question. When you mention name-based accessors, are you talking about loaded labels or what?
Something like that, yeah. So you can essentially do something like, or you could use it in conjunction with overloaded labels or something. But essentially, like if you have a product indexed by a code, then the normal way to index into that product would be by position, right? You're basically saying I want the second component out of that product. But since you now have record labels potentially associated with that product, and these record labels are known on the type level, you could also say, rather than saying I want the second component out of that product, I want the component that is labeled by this label. And you can actually write functions using this type level metadata that operate in this way, and you can use this to, for example, derive sort of lenses on the fly or something like that operate on a particular label. That is one option. But the sort of more powerful thing that gives you perhaps something extra is that the lenses that you would derive in this way do not necessarily work only on the original data type, but they may also work on sort of shape-compatible variants of that data type that have sort of the same number of fields but are somehow derived from it. And you could still like have convenient lenses or accessors available for them automatically.
Yeah, so if there is no more questions, then thank you.